So today we're going to continue with divide and conquer. I am going to make use a few times of the master theorem, which we discussed last lecture on Thursday. I went through the pain of actually kind of exactly computing this summation on Thursday to recover the master theorem, but pay close attention to homework 2, problem 2b, which just got released last night. What that says is if you have a geometric sum like this, 1 plus p squared plus plus p to the k, there are 3 cases. You're either dominated by the first term in the sum, by the last term, or all the terms are equal, they're all 1. And that's exactly basically what happened on Thursday, okay? So kind of as a shortcut for the future, kind of whenever you see these geometric series, you don't really need to exactly compute the answer if all you want to know is the answer up to a constant factor. You know that it's either dominated by the first, the last, or they're all equal. And it depends on whether p is bigger than 1, p is equal to 1, or p is less than 1. That's just a general phenomenon, okay? So if you got exhausted with all the arithmetic on Thursday, that arithmetic, you don't really need to do that arithmetic. There are shortcuts based on just looking at whether, these 3 cases for p. Anyway, you'll have some practice with that on homework 2, problem 2b. So today I want to talk more about divide and conquer. And I started to introduce one of the problems last time. So one of the problems specifically we're going to discuss today, we're going to discuss matrix multiplication, sorting, as well as median finding, or more generally, selection. Okay, so all of these will show divide and conquer algorithms for. So matrix multiplication. Okay, so I told you what the setup was. Your input is 2 n by n matrices, which I'll call x and y. And the goal is to compute z, which is x times y, okay, which is itself an n by n matrix. Right? And I said this last time. If this is x and this is y, and this is z, if you look at any given entry of z here, like for example, this is the ith row and the jth column, right? The way you get that, just the definition of matrix multiplication, is you take the ith row of x, and you take the jth column of y, and you take their dot product, right? Their dot product, how do you compute the dot product? It's a for loop. It's a for loop of length n, because there are n entries here. So you can get each entry of z in n time, or proportional to n time. There are n squared entries here. So to get all of them would take n cubed time, just using nested for loops. So theta n cubed time via nested for loops. So let's see how we can use, or whether we can use, divide and conquer to do better. Okay. So let's try to do something similar to Karatsuba's algorithm. Karatsuba's algorithm, right, you took the integer, a string of digits, and you just chopped it in half, and then used the distributive law to get something. So let's write here x. I can also break up its rows in half, but let's also break up its columns in half. So each one of these is n over 2 long, n over 2, n over 2, n over 2. And let me give these n over 2 by n over 2 submatrices names. So this is block A, block B, C, and D. Okay? And let me do the same thing for y. So this is y. Let's call these E, F, G, and H. And let me write that this product is equal to z. Okay. Now, how can I write the entries of z based on A, B, C, D, E, F, G, H? Well, it's also true that if you write the matrices in block form, just like you took the dot products of vectors there, you can basically take the dot product of blocks. Meaning, you basically take this collection of rows and dot it with this collection of columns, and you get something like AE plus BG. So the upper right entry here, this block is the dot product of the first block of rows with the first block of columns. Okay? And that's going to be AE plus BG. AE plus BG, right? And just to be clear, there's a product here, right? You're multiplying these things. Okay. And then to get the block, which is first row, or first collection of rows, second column, you take the first collection of rows here and the second collection of columns here and take their dot product. So that's AF plus BH. AF plus BH, and again, these are products. And then here you have CD plus CE plus DG. And then here you have CF plus DH. Right? So all of these are multiplications. Okay? So we started off wanting to do one multiplication, x times y, and now we find ourselves wanting to do 8 multiplications. 1, 2, 3, 4, 5, 6, 7, 8. So we can write a recurrence relation for the runtime that says the time it takes to multiply 2 n by n matrices is at most 8, because there are 8 recursive calls here, times the time it takes to multiply 2 it takes to multiply 2 n over 2 by n over 2 matrices, so T of n over 2. And then you have to put the answers together. What do you do to put the answers together? You add the results together, right? To add matrices is fast. It's just entry-wise addition. There are n squared pairs of entries you have to add. That takes n squared time, right? And so there are a bunch of additions here, but a constant number of matrix additions. So this is plus some constant times n squared. Okay? And we could draw out the recursion tree and calculate it from scratch, but we don't have to because this fits in with the format of the master theorem. So the master theorem says that, so what's A? A is 8, B is 2, D is 2. So A is 8, B is 2, D is 2, which implies A over B to the D. So 8 over 2 squared, that's bigger than 1. Right? So we have that our runtime is n to the log base b of a, which is n to the log base 2 of 8. So this implies T of n is big O of n to the log base 2 of 8, which is n cubed. Okay? Similar to Karatsuba, right? With Karatsuba, if we try to do the divide and conquer, the naive divide and conquer for integer multiplication, where we just broke into 2 parts and did 4 recursive multiplications, we didn't really gain anything. We ended up with an n squared algorithm, which we already have via the straightforward algorithm. So it's the same story here. If you just do the vanilla divide and conquer, you don't gain anything asymptotically compared to just using the kind of the straightforward algorithm that you first learned. Okay? But then, maybe I'm not sure, inspired by the fact that something is doable for integer multiplication, someone came along named Strawson and actually got something better. So Strawson, in 1969, he said the following thing. Okay, so this is going to look a little funky. let's compute not 8 recursive multiplications, but only 7. And these are the 7. So I'll write a couple of them, and I won't continue because it just looks kind of random. A times f minus h and let's P2 is going to be A plus B times H, and P3 is going to be C plus D times E, all the way down to P7 being something. So each of these involves one matrix-matrix multiplication on n over 2 by n over 2 matrices. Okay? And then what he showed is kind of once you have P1 up to P7, you can recover these entries by combining them. So what he says is this implies that this matrix Z that you want, if you write it as 4 blocks that are each n over 2 by n over 2, the top right block turns out to be P1 plus P2. Can we easily verify that? So you have AF minus AH plus AH, so the AH's cancel. So you have AF plus BH. Okay, that's true. It turns out, I'm not going to walk through all of this, but it turns out you do get exactly those expressions if you do these combinations. The upper left block is P4 plus P5, P4 plus P5 plus P6 minus P2. This is kind of arbitrary looking. Honestly, I don't think there's a really good way of coming up with this other than like trying to do some kind of brute force search with pruning. Okay? But it turns out that this exists. And later, people doing algebraic geometry managed to prove that there is no way to do this kind of setup with less than 7 multiplications to be able to combine them to get Z. Basically 7, it turns out 7 is possible. That's what Strawson showed. And later it was shown that you can't do less than 7. Okay? But at the end of the day, you get a recurrence that looks as follows. T of n is at most 7 times T of n over 2 plus O of n squared, right? Because again, you're doing these additions and subtractions of matrices. You're also doing a few more additions and subtractions here. But in total, you're only doing a constant number of them, right? So plus some constant times n squared, we can plug that into the master theorem. Instead of 8 over 2 squared, it's going to be 7 over 2 squared. That's still bigger than 1. So we're still in the pink case of the master theorem. So this implies that T of n is big O of n to the log base 2 of 7, which if you plug into a calculator is big O of n to the 2.807 something. Okay? Anyway, it's better than n cubed. So, right, the natural question then is, of course, can you do better? With integer multiplication, I told you, first we had Karatsuba, which got n to the roughly 1.585. That was n to the log base 2 of 3. Very soon after that, there was the Toom-Cook family of algorithms, which could get kind of n to the 1 plus epsilon for an arbitrarily small constant epsilon. So n to the 1.001. And kind of as of last year, we know n log n. So the log n part is kind of a small multiplicative factor. The dominant, the thing that's, the polynomial in n is linear, right? It's like linear in n times something small. And here, we're not going to get linear in n because the input itself has n squared entries. The output has n squared entries. But you could ask, did a similar story happen with matrix multiplication? Can we now do very close to n squared? And there were a sequence of works. I'm not going to write them all. But so we said Strawson in 69 got roughly n to the 2.807. It was a little worse than that. There were a bunch of papers after that, and then kind of humanity got stuck for a while until at Coppersmith and Winograd. So there are a bunch of papers I'm not writing. Then there was Coppersmith and Winograd. That was 1987. And they got n to the 2.3754770, something. Okay, and when I was in college and most of my time in grad school, that was kind of the best that humanity knew. And then there was a PhD thesis by this guy named Stothers. And what he could get was n to the 3.37, okay? And then you get improvement in the next digit, 368. Okay, and that was in 2010. And there was another paper around the same time. They actually, it came after, but it was done kind of independently of knowing about Stothers' work by Vasilevska-Williams. That's one person in 2012. And what she got was, again, n to the 2.37, 2873, something. And then the state of the art right now was 2 years after that by a guy named Francois Legal. That's 2014. And he got n to the 2.3728 639. Okay, so, if you're, just in case you didn't notice, this is the digit that changed, okay? And that's where, and note, all of these are pretty close to Coppersmith and Winograd, if you haven't noticed, but that's where we are right now, okay? So matrix multiplication is still, unlike integer multiplication, which is essentially a solved problem now, we still have no idea what the best algorithm is for matrix multiplication. And unfortunately, it's also true that kind of if you look at the Python source code, which we did on last week Tuesday, yeah? Do
you have an idea for what values of n does this start to become?
So what values of n are these algorithms better? There are some big constants out here. I don't know what they are, but what I can tell you is that I believe it's true that absolutely no one uses anything beyond Strawson. Like once you go beyond Strawson, the constants are very large. And even there, I think a lot of packages don't even use Strawson. They just use some optimized n-cubed algorithm. They use the n-cubed algorithm. So unfortunately, this hasn't had that much practical impact. But yeah, that's where we are. Any other questions? Okay. So that's it for matrix multiplication. I'm going to shift now to sorting, and I'll leave that board up there because we're gonna again, have some recurrence that fits the master theorem. So sorting, and specifically merge sort. So I believe everyone here should have seen merge sort in like 61B. Is that right? Okay. I'll just make sure that we're all refreshed on what it is. So merge sort, the idea is you have some array A. Okay. And what you do is you take the first half of A, okay, the first n over 2 elements in A. You recursively sort those. Then you take the last n over 2 elements of A, put them in an array, recursively sort those, and do a merge procedure, right? What's the merge procedure? The merge procedure, well, these are now two sorted arrays, and you have to merge them into one sorted array. How does that look? So here's one sorted array. Let's make some stuff up. 1, 5, 7, 8, 15, etc. And then I have another sorted array. Okay. and I want to merge them. And I'm not going to write the pseudocode. You've all seen this in 61B. But just so that we all remember, the idea is basically this two-finger method, right? So you always keep track of 2 pointers, one in B and one in C. They both start at the beginning. Right? So the point is, for the first thing in the sorted array, in the merged array, has to be the smallest in the union of the arrays. But there are only 2 options for who that could be. It's either the smallest in B or the smallest in C. Okay? So the invariant we're going to maintain is that we're going to have these 2 pointers, one into B and one into C, and they're always going to point into the candidate for who the next smallest person could possibly be. It's always going to be the next person in B or the next person in C. Right? So here, the smallest between, we just have to compare 1 and 2, and 1 is the smaller of them. So that's the next thing in our merged output. And then we can advance the finger. And then now we compare the fingers. There's 5 and 2. 2 is the next smallest. So now we can advance this finger, etc., right, until we merge. Our runtime is basically every time we write an output here, one of these fingers moves to the right. So in total, the total number of times we can move our fingers to the right is proportional to is like 2n, because there are n things here and n things here, or actually let's say n over 2 and n over 2 here. So you can merge 2 length n over 2 arrays in linear time, right? So just so that we're all again on the same page, so you have merge sort, which takes as input an array A. What does that do? I say B is merge sort on the first n over 2 elements. C is merge sort on the next n over 2 elements. And then I return merge BC. Okay? So again, we're going to write a recurrence that's, again, going to fit the master theorem. So our recurrence is T of n is at most we're doing 2 recursive merges, or 2 recursive merge sorts on arrays of size n over 2, and then we merge them. Merging them just takes Cn time. And again, that fits the master theorem. Is it pink, purple, or yellow? Yeah, we're in the purple category, right? So this is the exact same recurrence as Karatsuba, by the way. Right? No, it's not. What am I saying? No, that was 3. A is equal to 2, B is equal to 2, and D is equal to 1. So we look at A over B to the D. A over 2 to the 1, 2 over 2 to the 1 is equal to 1. So this is the middle case. This implies that T of n is equal to O of n log n. Right? N to the D times log n. D is 1. Okay? There is, by the way, I don't know if you saw this in 61B, like a way to iteratively implement merge sort as well, basically using a queue of lists. Okay. Did you see that in 61B? Okay. Not everyone raised their hand, so I don't. So, okay, let's just make sure we all remember that. And I think that also makes it clear that, again, makes it clear in another way that kind of this approach gets you n log n. So let me make up a fake array, which is, let's say that A is 8, 7, 6, 5, all the way down to 1. So what you do is you first create a queue. Queue is a queue, okay? It's a queue of lists where first you just put a bunch of singleton lists in there. So you put in 8, then you put in 7, then you put in 6, then you put in 5, 4, 3, 2, down to 1. And you're going to have log n phases. And in each phase, I mean, actually, your algorithm doesn't even need to know, you need to keep track of the phases. But basically what it's going to do is, as long as there are 2 elements in here, you're going to pop off the first 2 things in the queue, merge them, and then push it at the end of the queue. Right? So you pop off the 8 list, you pop off the 7 list, and then you put it back here, you push it to the end of the queue, and now it's the merge list 7, 8. Okay? And then you pop off the 6 and 5, merge them, put in 5, 6, etc. Okay? At some point, you're going to finish with all the size 1 lists, right? And then you're going to start popping off the size 2 and merging them. And then you're going to pop off the size 4s and merge them until you're finally down to 1 list, which is everything sorted. Okay? So the algorithm doesn't need to really keep track of phases, but we in the analysis can keep track of phases, where a phase is when the list size doubles compared to the previous phase. So in phase 1, all these lists were size 1. Okay? And how much time do we spend doing merges? Well, we spend time proportional to basically reading all these lists once, which is linear time. And then phase 2, again, we read all these lists once. We spend a total of n time, O of n time. So each phase we're spending linear time just reading in these lists and merging them. There are log n phases, so again, the total time is n log n. Okay? So that's an implementation without recursion. Who has heard that there is no faster sorting algorithm than n log n? Okay. Many of you have heard that. Okay. I want to clarify. Who's seen a proof of it? Who knows a proof of that fact? Okay. So the first thing I want to say is that it's not a fact because it's false. Okay. The fastest algorithms we have for sorting are, well, there's a deterministic algorithm that takes n log n time. And there's a randomized algorithm whose expected time is n times the square root of log n. Okay. Let me write that down. So Hahn, back in 2002, showed sorting in O of n log of n time. This is a deterministic algorithm. And then Hahn and Thorup together came up with an algorithm, also in 2002, later in the same year, that says you can do sorting in O of n times the square root of log n. This is a randomized algorithm. And we haven't talked about kind of randomized algorithms yet. What I mean by a randomized algorithm is that again, we're doing worst case analysis where we look at the worst case runtime of the algorithm over an input of size n. But the algorithm is allowed to make kind of random choices as it proceeds. So the algorithm is allowed to flip coins and then choose an action based on the coin flip outcome. This is an algorithm that is guaranteed to always sort correctly, okay? But its runtime is a random variable. And the expectation of that random variable is this, n times the square root of log n. So its expected runtime is that. So that's what's called the Las Vegas algorithm. Whenever you have an algorithm that's always correct, I don't expect you to remember this, it's fine, I'm just saying it for your own knowledge. Whenever you have a randomized algorithm that's always correct, okay, we call that a Las Vegas algorithm, but its runtime is random, is a random variable. Versus, there are some randomized algorithms that their runtime is always fast, but their correctness is a random variable. So like the algorithm's output might be wrong with 1% probability, okay? It's bounded, you can bound it, so it's wrong with 1% probability, it's right with 99% probability at least, but it's always fast, okay? So something that is of that nature is like sampling at the polls, right? Like which candidate do I think is going to win the next election? I don't actually ask, if it's a presidential election, I don't actually ask every single voter in the United States. I randomly sample a few voters. I ask them, who are you voting for? And then I try to estimate the winner based on the sample, right? So that's kind of a Monte Carlo approach where it's guaranteed to be fast, or fast meaning I don't have to call that many people in America, okay? However, its correctness is random, right? Like there is some, maybe it's very unlikely, there's some chance that every single person I randomly called was in political party A, So I got a skewed sample, right? So that's possible but unlikely. So that's a Monte Carlo algorithm. Again, I'm just saying this in case you ever hear those words in life and you want to know what they mean. We're not going to test you on Las Vegas versus Monte Carlo. But anyway, this is a Las Vegas algorithm. Okay, so anyway, some of you did say that you heard that. Oh, yes?
Sorry, do these algorithms make any restrictions or assumptions on their input? Or?
Okay, good. So do these algorithms make restrictions on their input? Okay, so sort of, but I would say not really. And what do I mean by that? So those of you who have heard that n log n is the best you can do for sorting, what people really mean when they say that is that if your model of computation, right, is that the only way your computer can interact with the entries in the array is compare them, okay, then provably, and we'll see, I'll show you a proof, provably you cannot do better than some constant times n log n as your runtime. You basically need to do proportional to n log n comparisons, okay? But I don't know what computers you're using, but at least my computer, right, I can do bitwise XOR, I can multiply entries. I mean, if the things I'm sorting fit in a machine word, right, computers, you're coding in C, you're not coding in some language that only allows comparisons between entries. Okay? If you're dealing with ints, let's say, so these are machine words, you can bitwise XOR, you can bitwise AND, you can multiply them, you can do all kinds of crazy stuff. You can treat them as indices into memory, right? If you allow yourself kind of the full power of what's called the word RAM model, like all the instructions that your architecture actually supports, then you can implement these algorithms, okay? And you might have already heard of some of these kinds of algorithms, like radix sort. Even if you haven't heard of radix sort, kind of a simpler algorithm is counting sort, right? Counting sort says, if I have n integers that I'm trying to sort, and all the integers are between 1 and b, I can sort them in time proportional to n plus b. How do I do that? Basically, I create an array of size b. I scan the input, and whenever I see an input in the array A that I'm trying to sort, like let's say that input is 5, I'll just throw that element into bucket 5 in my length b, right? So okay, let me actually just do counting sort down here. So let's say b is 5, and then n can be something big. So what I'm going to do is I'm going to allocate an array of size 5. And then here's A now, the array I'm trying to sort. All of these entries are between 1 and 5. So I'm going to look at them one by one. Oh, this is a 2, so I'm just going to put it in bucket 2. Like bucket 2 could just be a linked list, for example. Here's something that has value 4. I'm just going to put it in bucket 4. And then, once I'm done with the scan, I then just go here and scan it in order and output the entries in all of these buckets, right? So the total time is b to allocate this array plus n to scan this array, n plus b, right? So already, this is an algorithm that sorts integers that does not fit in the model of the comparison-based model, right? It's not just interacting with the entries of A via comparison. It's treating them as indices into memory, okay? So anyway, just be wary whenever you hear someone say things about optimality. Like, for example, later in the class, you're going to learn other algorithms like Prim and Kruskal for minimum spanning tree. That's going to be in a future week. Again, those algorithms are not, we actually have algorithms faster than that if you use the full power of the word RAM model, use the fact you can actually multiply integers and do all kinds of bitwise operations. So anyway, just thought I'd make you aware. Now, if you assume the comparison-based model, why then is n log n the best you can hope for? So I'm going to just restrict myself to a subset of all possible inputs to merge sort, or not to merge sort, but to your sorting algorithm. So pretend the input, it's an array of length n. It's some unknown permutation sigma of 1 up to n. Okay? So you know the algorithm, even if the algorithm knows that the input is some permutation of 1 up to n, if all it's allowed to do is compare the entries, it still can't beat n log n. Right? So I'm giving the algorithm more power. It knows that the input looks like this. But it doesn't know which permutation. Okay. So the algorithm, whatever it does, at some point it's going to do a comparison. Right? It's going to say like, let's say there's no reason for it to ever do equality comparisons because it knows that all the entries are distinct. So it knows that it knows the answer to any equality comparison. It knows that they're not equal. So it only makes sense for the algorithm to do less than and greater than comparisons. So at some point, it's going to, and that's equivalent to saying it only does less than comparisons, right? Because it could just, if it's going to, is I greater than j, that's the same thing as saying is j less than I. So just pretend it's always doing less than comparisons. So at some point, at the beginning, it's going to ask, is A5 less than A7? That's the comparison it's going to do. And there are only two answers that are possible, yes or no. So it's going to branch. Either the answer is no, or the answer is yes. And based on what happens, the algorithm is going to do something next. And it's going to ask, well, how about A1 versus A7? Is that less than A7? Who knows what it's going to do? But the point is, it's basically just doing this kind of, there's this decision tree that describes the behavior of the algorithm on any input. Okay? Now, what are the leaves of this tree correspond to the algorithm knowing what the answer is, right? Once it stops asking questions, that's because it knows which permutation it found. Okay? Now, in some branches of this tree, it might stop earlier than other branches, because maybe in some cases it can find the answer in like 20 comparisons, but some cases it does 50. I'm just going to assume that all the leaves are at the same depth. Namely, no matter what the input is, it always takes the same amount of comparisons to get to the answer. And I can assume that without loss of generality. Why? Because let's say that the maximum depth in this tree is t, where t is time, to get down to a leaf. If there's any leaf that's higher than t, I'll just modify the algorithm to just keep making dummy questions until it's actually at depth t. It knows what the answer is. So let it keep asking dummy questions even though it already knows the answer and get me down to t. Okay? So now what do I have? I have a complete binary tree of height t, where t is the runtime of this algorithm. Well, the runtime might even be more than t, right? T is just the number of comparisons it's doing. Maybe then it looks at the comparisons it's done so far and spends a lot of time figuring out what comparison to do next. That's only going to make it slower. Right? So the runtime is certainly at least t. It might be much more than t, but it's certainly at least t. Okay? How many leaves are in this tree? 2 to the t, because it's a complete binary tree of depth t. Okay? So there are 2 to the t leaves in this tree. Every permutation had better have its own leaf somewhere. Right? Because if the permutation is 1, 3, 2, right? The algorithm had better correctly sort. So the algorithm needs to know that, that it is 1, 3, 2. So it better end up at a leaf that corresponds to 1, 3, 2, right? No two different permutations can arrive at the same leaf, because that means that the algorithm is wrong in at least one of them. Does that make sense? So the number of leaves had better be at least the number of permutations on 1 to n. Well, this is n factorial. This is 2 to the t. So we just said 2 to the t is at least n factorial. Take logs of them. That implies t is at least the log base 2 of n factorial. And I think this was a problem on PSET 1, on homework 1. Right? This is at least n times the natural log of n, kind of minus some smaller stuff, minus some O of n terms. So in other words, this is omega n log n. Okay. Yeah.
Why can you say that you don't lose generality by adding all those dummy subtrees? It would be pretty different if you had a tree that only has one really, really long branch and everything else.
What you said, why? So, okay, so what you're asking is the following. I said originally the tree might have leaves at different depths. And I said, let's just pad it out to make the shallower people deeper so that everyone's at the same depth. Why is that without loss of generality? The point is, the way that I define the runtime of an algorithm is the worst case runtime over all inputs of size n. So if there's an algorithm that has some people at a really deep depth, t, but some people at a very shallow depth, like 5, even if I deepen the 5s all the way down to t, I haven't changed the worst case runtime. Right? So doing this filling out of the tree doesn't change the worst case runtime. That's the point. Okay, so anyway, that's the proof that if you're in a comparison-based model, you cannot do better than n log n as your runtime. Yeah?
What do you mean that every leap corresponds to a permutation if you're just doing random comparisons throughout the tree?
Yeah, so I guess, okay, so what do I mean by every leaf has to correspond to a permutation? What I mean is the following. So maybe let me say it a little differently. Take the permutation 1, 2, 3, 4. Okay? Let's say that were your input. Okay? Then your algorithm is going to do some comparisons, and it's going to end up at some leaf. Let's say it ends up at this leaf. Now let's look at a different permutation, 1, 4, 3, 2. It's again going to do some questions, right, some comparisons, and end up at some leaf. Can it end up at this leaf? No, it cannot end up at the same leaf as another permutation, because what does this leaf correspond to, right? Like, at the end of the day, the algorithm has to sort, right? So it has to, like, permute the entries of the input, right? So if it permutes the entries of the input one way for 1, 2, 3, 4, and it lands at the same leaf for 1, 4, 3, 2, it means it's going to permute these entries in the same way it permuted these entries. But like that permutation of the entries is not going to be right for both. Right? Each different permutation needs its own kind of inverse permutation of the entries. Yeah, so I guess, right, that's right. Yeah. Okay? So maybe another way of saying it is look at all the n factorial permutations here. For each one, run it through this decision tree and ask yourself, where would I end up? So 1, 2, 3, 4 would end up here. 1, 4, 3, 2 would end up here, etc. All of these end up locations have to be different, which means that there are at least n factorial leaves here. Yeah?
So for the input, are we considering a single list, like one sigma of that permutation, or is it like all permutations that the input will give?
No, the input is a single array, and that array is going to be some permutation of 1 up to n.
So one leaf is going to be that corresponding to that one sigma, is that one permutation?
So any permutation, when you feed it as input to this supposed algorithm it's going to run through the decision tree and end up at a leaf. Every input is going to end up at a leaf. Yeah. Okay. Yeah. Why are there more leaves than permutations? Oh, can there be? Can there be more leaves than permutations? I mean, it could be. That's possible if you're out. For example, your algorithm could ask some like redundant questions. I don't have any control over this algorithm, right? You gave me an algorithm that you said sorts. I'm trying to prove to you that this algorithm, no matter what it was, takes at least n log n time. Your algorithm could do a bunch of redundant stuff, right? It could do all comparisons. It could compare 1 with 2, 1 with 3, 1 with 4, 1 with n. It could then compare 2 with 1, 2 with 3, 2 with 4, 2 with n. It could do n squared comparisons, right? A lot of those are redundant. So it's going to have 2 to the n squared leaves, right? Does that make sense? So that's why. I mean, because you have a non-optimal algorithm, basically. Okay, so I think let's move on. Maybe enough about sorting. I want to do the one last topic for today, which is related to sorting. It's median finding and selection. And then Thursday is going to be our final divide and conquer lecture on the fast Fourier transform. Okay. So again, you're given as input an array of size n, together with an integer k, which is between 1 and n. And the goal is to output the kth smallest entry of A. The median would be k is n over 2, right? Okay. So given that you know merge sort, the simplest solution to this is sort the array A, and then just return the n over 2th entry in the sorted array. Okay? That would be a valid n log n time algorithm or an n root log n time algorithm, okay, depending on how you sort. We're going to try and do this in linear time. In fact, we are going to do it in linear time. And kind of the motivation, the motivating algorithm for why we expect to be able to do it in linear time is the following. So there's an algorithm called quick select, which we're not going to analyze formally today. But the way that algorithm works is as follows. Who's heard of quick sort? Who's heard of quick select? Fewer people, but it's a similar concept. So here's my array of size n. Okay? How does quick sort work? Many of you have heard of quick sort. Quick sort picks a random element and calls it the pivot, right? And then you compare each entry in the array with the pivot. And then what you do is you move everyone who's smaller than the pivot to the left, and you move everyone who's bigger than the pivot to the right. You recursively sort the left, you recursively sort the right, and now you have the whole sorted array. That's quick sort. Quick select is similar. You pick a random pivot. You compare everyone to move into people who are smaller than the pivot and bigger than the pivot. And now the point is you don't have to recursively call yourself on both the left and the right. You only need to recursively call select on one of them, right? Because let's say that you found out the pivot was actually the 107th smallest, to make something up. Right? So the point is, you know the rank of the pivot because you compared him with everyone. So you know how many people are less than the pivot, you know how many people are bigger than the pivot. So you know his rank. And then now, if you're looking for the kth smallest element, well, if k is 107, you just return him. If k is less than 107, you only have to recurse on the left. And if k is bigger than 107, you only have to recurse on the right. So it's like quick sort, but you only have to recurse on one side, not both sides. So that's quick select. Okay. And kind of the hope with basically what you want to do, ideally what you want to do, is you want to have a recurrence. So your desire is to have a recurrence that looks like t of n is at most t of n over 2 plus c times n. C times n is compare the pivot with everyone. And then t of n over 2 is, I hope, my desire is that the pivot is actually the median. Right? Because if the pivot is the median, then no matter which side I recurse on, that side has size n over 2. If the pivot were like far away from the median, then I might get unlucky and have to recurse on the bigger side. And this, because of the master theorem, solves to linear. This is O of n. So it's not n log n, it's just O of n, right? So it's a linear time algorithm. You have to be a little careful. I mean, this is not a valid analysis of quick select, right? Because the pivot, you're picking a uniformly random entry in the array. It's probably not going to be exactly the median. Okay? But on the flip side, it's probably not going to be, what's the bad case? The bad case is that the pivot is actually, let's say, the smallest element, or the second smallest, or the third smallest, or maybe it's the largest element. right? The bad case is that the pivot is kind of either really small or it's really large. It's in kind of one of these two regions at the end. Because if that's the case, let's say your pivot is here in the sorted order, you might end up having to recurse on all of this. So you haven't really cut down the problem a lot. Kind of in the extreme case, if you're unlucky and the pivot is always the smallest element, you're going to get something that looks like T of n is at most T of n minus 1 plus Cn. And that solves to n squared. Right? So if you're unlucky and the pivot is always on one of the endpoints, you get an n squared algorithm, which is not great. Okay. So anyway, that's quick select. I will say that, again, it's not going to be true that it's very unlikely that your pivot is always going to be exactly the median, but it's probably usually going to be true that your pivot is, say, not in the bottom 10% and not in the top 10%. Your pivot is very likely to be kind of in the middle 80%. In fact, the likelihood of that is 8/10. Okay? So is 80%. So 80% of the time, which is pretty good, your pivot is somewhere in here, which means, instead of n over 2, you might get something like 8n over 10, but that still solves to linear by the master theorem. So you don't really need the median to make the algorithm work. You just need something that's not the median. This is not a valid analysis of quick select because this number here is actually a random variable. So you need to actually do some kind of probabilistic analysis to really have a formal analysis of quick select, which we're not going to do today. But it's possible to do such an analysis of quick select and to get that the expected runtime of quick select is linear, is O of n. Okay. So anyway, now that I've said a million times that we're not going to do quick select, I want to do something that actually we are going to be able to analyze. It's going to be a completely deterministic algorithm. And this algorithm, the design of this algorithm, is motivated by this observation that as long as we can get a pivot that's in the middle, say 80% or 70% or something like that, that's still good enough for us. Okay? That's still good enough to make this recurrent solve to linear by the master theorem. So now the name of the game is, how can I design an algorithm that's guaranteed to output someone who's a good pivot, who's in that middle 80%, let's say. Okay. I do want to make one simplifying assumption about this problem, which again is going to be without loss of generality. So without loss of generality, A has no duplicate entries. The algorithm can handle the case, just like quick select can handle the case where you don't have duplicate entries. I mean, for example, let's say you ran quick select on the array which is 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay? So you pick a random element, okay, as your pivot, it's going to be 1. Okay? Is it going to be, now you pivot around 1, basically everyone is equal, who goes on the left and the right? I mean, there are different implementations that can handle this. One is you alternate putting them left or right. Another one is you keep track explicitly of the people who are exactly equal to the pivot and deal with them separately. All of this works. If you coded it, it's just like an extra, a couple of if statements in your code. It's manageable. But let me show you a trick so that you don't have to deal with it at all. Okay? And the trick is just, I have my initial array A. Let me create a new array B, where B is the array of pairs. It's A1, comma 1, A2, comma 2, up to AN, comma N. And then I'll just solve the problem on B. Okay? And now and what's the comparison for, I do basically lexicographic comparison. So when someone asks me to compare two entries in B, those two entries are pairs. I first compare the first element in the pair. And if they're not equal, great, that decides my comparison for me. If they are equal, I just compare the second element in the pair. And those are guaranteed to be different, because all the second elements in these pairs are all different. Right? So what this reduction, this is basically, we'll see more about reductions later in the class, especially when we talk about NP hardness, etc. But what I've just shown you is, if you have an algorithm for quick select that works in the comparison model, or not for quick select, for select, that works in the comparison model, okay, that only works when the entries are distinct. I can use that algorithm in a black box way to solve the problem even when they aren't promised to be distinct by doing this transformation. Right? So I'll take my input, I'll do this transformation, and then I'll feed B into the algorithm. Okay? So from now on, we can just pretend that all the entries in the array are distinct. I don't want to have to deal, it is possible to deal with it, I just don't want to have to deal with managing equal entries to the pivot separately. Okay? Actually, good. So now, so from now on, A has all distinct entries. Okay? Okay, so now what's this algorithm going to be? Oh, can you hear me back there on the camera? Hello? Oh, videographer. Okay. Can you tap him? Can you still hear me? Is the mic working well? Okay. Let me just adjust this because it doesn't look good. Okay. All right. So what's the algorithm? So I'm going to basically do the quick select algorithm. I'm going to pick a pivot, and then I'm going to figure out which side of the pivot to recurse on. The question is just, how do I pick the pivot? So here's how I pick the pivot. Here's my array A. It has n entries. Okay, now here's where things get a little weird, but I will justify the weirdness when we analyze this algorithm. The weirdness is not out of nowhere. So I'm going to group the entries into blocks of size 5. So I'll take the first 5 entries in the array. I'll take the next 5 entries in the array, the next 5, the next 5, etc. So basically there are n over 5 groups. And then in each group, I'm going to find the median of that group. Okay? How do I do it? I can basically do whatever I want because it's a constant size problem. So no matter what I do, it's going to take O of 1 time. So I'll merge sort that group of size 5 and then pull out the median from that. That takes me 5 log 5. It takes me constant time. Okay? So now I have the median of this group, which, let's say even though it might not be that way in the input, let me draw, all these are the medians of their groups. And then I recursively call select on this to find the median of this. Okay. So I call select recursively on this with k being n over 10, because n is now n over 5. Median is then the halfway mark of that, which is n over 10. And then that's going to give me the median of this, which is, let's say that's the median of these n over 5 elements. That's going to be my pivot. Okay? And then I'm going to use that pivot to then do the quick select kind of approach. Okay? So in case we're not all clear on what the algorithm is, so select takes as input an array A together with k, First step is break A into groups of size 5 each. B is an array which is the array of medians in each group. P is going to be my pivot. P is going to be select on B, with K being n over 10. And then now I'm going to do a pivot. So I'm going to say that, let's say that L are the set of things that are less than P, and R are the set of things that are greater than P. So I just made up this notation, but you can basically get L and R from a linear scan over the array. And then I need to recurse again. So if K is equal to the size of L plus 1, return P, right? Because the rank of P is the L plus 1 of the smallest element in the array, because there are L things less than it, and then there are R things bigger than it. So if K is L plus 1, return P. Otherwise, if K is less than or equal to L, return select L K. Otherwise, that means K is bigger than L plus 1. Otherwise, I'm going to return select R, and then K has to change. It's going to be K minus L minus 1. Right? Because even the smallest thing in R is bigger than L plus 1 things in the original array A. It's bigger than L, all of L, and it's also bigger than the pivot P. That's L plus 1 items. So if you're let's just give these some numbers, right? Like let's say that L and R are each size 10, right? So if I'm looking for the 12th smallest element in the array, well, that 12th smallest element is bigger than everything in L, and it's bigger than P, so it's bigger than 11 things. So that means it's the first smallest and what's left over. Okay, so that's all I'm doing with the subtraction of L minus 1. Okay? Okay. So good. So that's the algorithm. Let's try to analyze the runtime of this algorithm. Let's try to write a recurrence relation. So the runtime on inputs of size n, the worst case runtime, is at most, okay, so I break up A into groups of size 5, and then I compute medians in each group. Okay, so, there's some linear time procedure to break it up into these groups. And then, how many groups are there? There are n over 5 groups, right? And in each group, I find the median. That takes constant time per group. So times constant time per group. So that's, again, O of n. Okay. And then I have to recursively call myself on this array B. B has size n over 5. Plus t of n over 5. Then I have to pivot around P. That takes linear time. Plus O of n. Then I have to call myself on either L or R. What can I say about the size of L, the sizes of L and R? So this is where the magic of 5 is going to come into play. What do I know about this median of medians, right? I took the median in each group of size 5, and I took those medians, and this person is the median of those medians. He is bigger than the smaller 2 people in his group. So he's bigger than these 2 people in his group. He's also bigger than all the medians to the left of him. So he's bigger than this median, he's bigger than this median. But this median is bigger than these 2 people too. And this median is also bigger than these 2 people. So I am guaranteed that this person here is bigger than how many people? Well, in half the groups, he's bigger than 3 people. How many groups are there? So half the groups, there are n over 5 groups. He's bigger than 3 people. But this is just 3n over 10. So guaranteed, L has size at least 3n over 10, and R also has size at least 3n over 10, which also means that L has size at most 7n over 10, and R has size at most 7n over 10. Neither L nor R can be bigger than 7n over 10 in size. So plus T of 7n over 10, no matter which case I'm in for this recursive call. So let's just clean this up a little bit. This is at most T of n over 5 plus T of 7 over n over 10 plus some constant times n. Okay. Unfortunately, this does not fit into the framework of the master theorem. But let's just try to solve this kind of in an ad hoc way. And the way I'm going to solve it is by using strong induction. Okay. So this is one of those like guess and check methods. I'll just guess that the answer is linear, and then I'll try to prove it by induction. And if it succeeds, then yay, it's linear. Okay, so. And now you'll see why, like, what if instead, you'll see in the analysis, the fact that we broke into groups of size 5 is not super important. It just has to be any odd integer which is at least 5. Okay, so if we had broken into groups of size 9, that would have also worked. If we had broken into groups of size 3, that would not work. Okay? And when I say it would not work, I mean, it would still give the right answer, right? I mean, because no matter what pivot you choose, you get the right answer, right? This algorithm works no matter what your pivot is. Even if you choose the absolute minimum of the array, it'll just be n squared time. So when I say works, you'll get linear time. If you use these groups of size 5 or 7 or 9 or 11, you'll get linear time. If you use groups of size 3, you're unfortunately not going to get linear time. It'll give a correct algorithm. It'll just be slower. So let me convince you that, at least with groups of size 5, you do actually get linear time. So let's just guess that T of n is at most b times n. And I'm going to be a slightly sloppy in this proof in that, like, in reality, I really need to say something like the seal of n over 5 and like the seal of 7n over 10. I'm just going to pretend that all along the way everything is perfectly divisible, which is not actually going to be possible because how's it going to be always divisible by 5 and 10 over 7? Okay, but let's just pretend that there are no seals just to make our lives a little easier. So let's guess that this is true for some constant b, and let's see can we choose a constant b that actually makes this proof work. Okay, so like now that we guessed that, let's try to prove it via induction. So the base case let's say the base case has to handle the end of the recursion. Let's say that's n equals 1. our runtime when n equals 1 is like 1. So this holds as long as b is at least 1. So okay, so far we have to set b to be at least 1 to make this true. Already this is a little bit bogus because really, notice that we said things like break into groups of size 5. What if the array has what if the array has size less than 5? What if the array has size 4? So really the base case should be like n is less than 5. Okay? In which case, you need to make sure that b is big enough so that this inequality holds for n being 1, 2, 3, or 4. But whatever, just choose b to be a really big constant so that it holds even for those 4 values of n. Okay? Or some other big constant. What about the inductive step? As long as I can prove, so I'm going to assume, this is strong induction, right? Strong induction means you assume the hypothesis is true for all values that are less than n. Like induction is usually like n implies n plus 1. Strong induction is for all values less than n plus 1, together they imply n plus 1. So I'm going to use strong induction because I want to say it's going to be, I'm going to assume by the inductive hypothesis that it's true for both n over 5 and for 7n over 10. Okay, so it's true for both of them. Both of them are at most b times those values of n. So I just want to verify that this expression is less than or equal to b times n. So is it true that b times n over 5 plus b times 7n over 10, is it true that plus c times n, is it true that this is at most b times n? Is that true? Let's rearrange this. I can, first of all, just get rid of all the n's. N's are everywhere. And let me subtract off the things that depend on b to here. So this is now, is it true that b times 1 minus 1/5 minus 7 over 10, is it true that that's at least c? 1 over 5 is also known as 2 over 10. And 1 minus 2/10 minus 7/10 is 1/10. Right? So b over 10, what we're asking is b over 10 at least c? Well, yes, now it is because I'll just set it to be 10 times c. Okay? So we're done. So our induction goes through if we set b to be 10 times c. Right? And this is exactly the place that breaks down if you try to do groups of size 3. If you try to do groups of size 3, I guess we have 4 minutes. Let's reason about it. So what can I say? What I can say is this guy is bigger than 2 elements in half the groups. So I'm going to have a half times n over 3 times 2. Right? I'm going to have a half times n over 3 times 2, which is n over 3. He's guaranteed to be bigger than n over 3 elements, and he's guaranteed to be smaller than at least n over 3 elements. Right? Which means that L and R each have size at most 2n over 3. So that 7n over 10 is going to get replaced with 2n over 3. And that n over 5 is going to get replaced with the number of groups now, which is n over 3. So if you try to plug that in here, you're going to have something like, let me do it in a different color because this is a fake analysis of something that doesn't work. You're going to want to have that b times 1 minus, this 1/5 becomes 1/3. 1/3 minus 2/3, you're going to want that to be at least c. Okay, there's nothing you can do. This is saying c is non-positive. Okay, so c is, you can't make c negative. You don't have any control of c. C is c is the kind of time it takes to do all this linear time stuff, right? Like to to do the partitioning and to compute the medians of the groups, etc. So unfortunately, if you choose the groups of size 3, you just don't get anything. Does that make sense? Okay. So that's it for today, and then Thursday we'll have the last lecture on divide and conquer, and then next week you'll start hearing from Professor Chiesa.